Welcome to today's video where we dive deep into two groundbreaking papers that revolutionized vision language AI. We are talking about DeepMind's Flamingo and its open source counterpart, OpenFlamingo. These models represent a massive leap forward in how artificial intelligence can understand both images and text together. By the end of this video, you will understand exactly how these systems work, why they matter, and what makes them different from everything that came before. So, what exactly is Flamingo? Imagine showing an AI model just a handful of examples, maybe 4 or 5 images with captions, and then asking it to perform a completely new task. That is exactly what Flamingo does. It is a visual language model that can rapidly adapt to novel tasks using only a few examples. This is called few-shot learning, and Flamingo excels at it. The model can handle sequences of arbitrarily interleaved visual and textual data, meaning you can mix images, videos, and text in any order, and the model will understand the context. What is truly remarkable is that Flamingo achieves state-of-the-art performance on numerous benchmarks, often outperforming models that were fine-tuned on thousands of times more data. The largest version, Flamingo 80 billion parameters, set new records across 16 different vision language tasks when it was released in 2022. Now, let's talk architecture. This is where things get really interesting. Flamingo's genius lies in how it bridges two worlds. On one side, you have powerful pre-trained vision models that understand images. On the other side, you have large language models that understand text. Flamingo connects these frozen, pre-trained components with innovative architectural additions. First, images or videos are processed by a frozen vision encoder, specifically a normalizer-free ResNet F6 model pre-trained with contrastive learning. This encoder converts visual input into a spatial grid of features. But here's the problem. This grid can be huge, especially for videos. Processing all these features directly would be computationally prohibitive. This is where the perceiver resampler comes in. The perceiver resampler is a brilliant piece of engineering. It takes a variable number of visual features and outputs a fixed number of visual tokens, always 64 tokens, regardless of input size. It does this using a cross-attention mechanism with learnable latent queries. Think of it like a smart compression system that preserves the most important visual information while reducing computational complexity. The second key innovation is how Flamingo conditions the language model on visual information. Between the frozen language model layers, Flamingo inserts newly initialized gated cross-attention dense layers. These layers allow the language model to attend to visual tokens while generating text. The gating mechanism is crucial. Each cross-attention layer has a learnable parameter called alpha, initialized to 0 and wrapped in a tan-hatch activation. This means that at the start of training, the added layers have 0 impact, preserving the language model's existing capabilities. As training progresses, the alpha parameters learn how much visual information to incorporate. This design prevents catastrophic forgetting, where the model would lose its language abilities while learning to process vision. The cross-attention layers are strategically placed. For the largest model, they appear every 7th language model layer. This balances computational efficiency with expressive power. Training Flamingo required a massive and diverse dataset. The model was trained on 3 types of data. First, multimodal massive web, or M3W, consisting of 43 million web pages with interleaved images and text. Second, A-line, a dataset of 1.8 billion image-text pairs. Third, VTP, 27 million video-text pairs. This diverse mixture is critical. The interleaved sequences from M3W teach the model how to handle multiple images in context, which is essential for few-shot learning. The paired data from A-line and VTP provides strong vision-language alignment. During training, the vision encoder and language models stay completely frozen. Only the perceiver resampler and the gated cross-attention layers are trained. This approach is computationally efficient and prevents the model from forgetting its pre-trained knowledge. The training objective is simple: predict the next token of text given all previous text tokens and visual inputs. Different datasets get different loss weights, with M3W weighted at 1 and A-line at 0.2. The results speak for themselves. Flamingo 80 billion achieved new state-of-the-art few-shot performance on 9 out of 16 benchmarks. On 6 tasks, it actually outperformed fine-tuned models despite using only 32 examples compared to thousands or millions of training samples. Let's look at specific numbers. On Coco captioning, Flamingo 9 billion reached 79.4 CIDR score with 0 shots and 93.1 with 4 shots. On VQA2, it achieved 51.8% accuracy with 0 shots and 56.3 with 4 shots. On OKVQA, which requires external knowledge, Flamingo scored 44.7% with 0 shots and 49.3 with 4 shots. These numbers might not sound huge, but remember, the model receives no task-specific training. It learns purely from in-context examples. When you give it 32 examples, performance improves dramatically. On Coco, 32-shot performance reaches 106.3 CIDR score, surpassing many fine-tuned baselines. Now, what makes Flamingo truly special is how it handles multiple images. Traditional vision language models process one image at a time. Flamingo can handle sequences with many images interleaved with text. The key is the masking strategy. At each text token, the model only attends to the visual tokens from the most recent image, not all previous images. However, information from all images is still accessible through the language model's self-attention. This design allows the model to generalize to any number of images at inference time, even though training sequences contained at most 5 images. In practice, Flamingo benefits from up to 32 in-context examples. Now let's discuss the ablation studies, which reveal what really matters. Removing the interleaved M3W dataset causes a 17% performance drop. Without it, the model can't learn effective few-shot capabilities. Removing image-text pairs causes a 9.8% drop, showing these are also important. Training without the tan-hatch gating reduces performance by 4.2% and causes training instabilities. Using vanilla cross-attention instead of gated cross-attention hurts performance. The perceiver resampler outperforms both MLP and vanilla transformer alternatives for connecting vision and language. Perhaps most importantly, freezing the language model is crucial. Fine-tuning the language model during training causes an 8% performance drop due to catastrophic forgetting. Flamingo's impact on the field has been enormous. It demonstrated that few-shot learning works for multimodal tasks, not just language. It showed that strategic use of frozen components enables efficient training of huge models. The gated cross-attention mechanism has been adopted by many subsequent vision language models. The ability to handle interleaved image-text sequences opened new possibilities for multimodal dialogue and complex reasoning. However, Flamingo has limitations. It inherits weaknesses from its language model backbone, including potential hallucinations and poor extrapolation beyond training sequence lengths. Classification performance lags behind specialized contrastive models like CLIP. In-context learning becomes computationally expensive with many examples. The model was trained on web data without explicit safety filtering, raising concerns about biased or harmful outputs. This brings us to OpenFlamingo, the open-source effort to replicate Flamingo. Released in 2023 by researchers at the University of Washington and other institutions, OpenFlamingo aimed to democratize access to this technology. The architecture closely follows Flamingo's design, with frozen vision encoders and language models connected by perceiver resamplers and cross-attention layers. However, OpenFlamingo uses different components. For vision encoding, it uses CLIP-VIT L.14 instead of NFNet. For language models, it uses open-source options like MPT and Red Pajama instead of Chinchilla. OpenFlamingo models range from 3 billion to 9 billion parameters. Training data also differs significantly. Instead of the proprietary M3W dataset, OpenFlamingo uses multimodal C4, an open-source dataset of 101 million interleaved sequences. Instead of A-Line, it uses Leon 2B, a publicly available dataset of 2 billion image-text pairs. They also experimented with synthetic data generated by ChatGPT, creating 417,000 sequences. Training used 60 million interleaved examples and 120 million image-text pairs, taking approximately 15 days on 64 GPUs. The results are impressive for an open-source effort. OpenFlamingo 9 billion achieves 89% of Flamingo 9 billion's performance on average across 7 benchmarks. On some tasks, like VQA2 and Coco captioning, OpenFlamingo nearly matches or even slightly exceeds Flamingo's zero-shot performance. However, gaps remain on tasks requiring external knowledge like OKVQA and text reading like TextVQA. OpenFlamingo shows stronger performance with few-shot examples than in zero-shot settings, but the rate of improvement with more shots is slower than Flamingo. One interesting finding is that instruction-tuned language backbones improve performance, especially for the 4 billion parameter models. Comparing the two papers reveal important insights. DeepMind had access to proprietary higher-quality datasets like M3W and A-Line, while OpenFlamingo relied on public alternatives that may have more noise. DeepMind used custom vision encoders trained specifically for their needs, while OpenFlamingo used off-the-shelf clip models. Flamingo used the powerful 70 billion parameter chinchilla language model, while OpenFlamingo's largest model uses 7 billion parameter MPT. Despite these differences, OpenFlamingo demonstrates that the core architectural ideas are sound and can be replicated with open components. The open source release has enabled numerous downstream applications and research projects.
The practical implications are significant. These models enable rapid prototyping of vision language applications without expensive fine-tuning. They can handle diverse tasks like captioning, visual question answering, visual dialogue, and image classification within a single model. The few-shot learning capability makes them accessible to users without large labeled datasets. They provide a foundation for further research into multimodal reasoning and in-context learning. Both papers demonstrate that bridging vision and language effectively requires careful architectural design. The perceiver resampler elegantly solves the variable size input problem. Gated cross-attention allows learning new capabilities while preserving existing knowledge. Training on diverse data mixtures is crucial for generalization. Freezing pre-trained components enables efficient training of massive models. The interleave data format enables powerful in-context learning. Looking forward, several research directions emerge. Improving performance on knowledge-intensive tasks like OKVQA remains challenging. Scaling to even larger models while maintaining efficiency is an active area. Incorporating safety considerations and bias mitigation into training is crucial. Extending these architectures to support video understanding natively, not just as frame sequences. Exploring how these models can be combined with other AI systems for embodied agents and robotics. The journey from Flamingo to OpenFlamingo illustrates both the power of breakthrough research and the importance of open science. DeepMind's Flamingo showed what is possible with cutting-edge resources and proprietary data. OpenFlamingo proved that the core ideas can be democratized, enabling broader access and innovation. Together, these papers have shaped how we think about vision language AI and few-shot multimodal learning. As we continue to push the boundaries of what AI can do, the principles demonstrated by these models, bridging modalities, preserving knowledge, learning from context, will remain fundamental. Thank you so much for watching this deep dive into Flamingo and OpenFlamingo. If you found this explanation helpful, please hit that like button and subscribe to the channel for more state-of-the-art AI paper reviews. Drop a comment below if you have questions or want to see other papers explained. Until next time, keep learning and stay curious about AI.